this differential rotation is thought to act as a mechanism to stretch the field lines by the so-called omega effect, which will take poloidal field lines like this, stretch them in this direction more than here, and the equator more than here. So you see that you stretch the field line and you create a component in the toroidal direction at the end of this omega mechanism. And you want to, of course, to recreate from your toroidal field, poloidal field, and this is something which is a little bit less understood. There are some possibilities that the convective motion could act to do so. So it would be called the alpha effect. This is a 3D effect, really stretching and twisting the field lines so they can recreate the poloidal component. And there's also something else, which is called the Baker-Clayton mechanism, which is due to the small tilt angle that the emerging region creates with respect to the east-west direction. So you will have bipolar spots emerging with a small tilt angle with respect to the east-west direction. This is a Joyce law we talked about yesterday. And this could be also responsible for the regeneration of poloidal field, this small component. So, yeah, this is more or less the simple picture, but what could be the responsible for permanent regeneration of magnetic field inside the sun? So this is not very important. So we have a procedure which I won't talk about, mean field approximation, which enables us to model these dynamo processes by these two coupled equations. A is the poloidal potential, that is here, and Bz is a toroidal field. So this is a simple model we're going to look at and try to do the variational assimilation on this. So, this is the alpha effect. So this alpha effect takes the toroidal field to regenerate poloidal field. Here is the omega effect. V is the toroidal velocity. So you shear your poloidal field to recreate toroidal field, and this is just a diffusion of the field. Right, so this is a kinematic dynamo. We won't have any Navier-Stokes equation governing the evolution of V. We just prescribe our velocity and see how our magnetic energy grows in time when we choose the right parameters for the strength of V, alpha, and eta. So this is the shape. This is the shape of omega, of alpha that we are using here. This is maybe not very important. So just to show you some examples of what it gives. So this is a case where we have these values for the parameters, and we have a growing magnetic energy in this case. With time, this is B squared. So we have an oscillatory field and exponentially growing. This is a case where it's quite close to the threshold for the dynamo to be excited. So the growth is not very important, but very fast. And this is the reconstructed butterfly diagram that we can get in this. In this model, so if you plot the contours of the toroidal field in time, and this is the model latitude, you get a reversal of the field as we can have in the observed butterfly diagram.
What's the time unit?
The time unit is just arbitrary. It seems a number of time steps, so it's not nothing. It's really.
It's not years.
No, it's not years. So it's not at all made fit exactly what we have in the sun. But of course, if you tune the parameters, you can easily have something which resembles the time scales.
What units for omega and alpha?
This is without dimensions, so it's.
What are units for?
I mean, radius is 1, right? And what is
alpha is
Radius is 1 and
velocity.
What?
Alpha is a velocity. Omega is angular velocity.
No, I mean in terms of non-dimensional, you have some numbers here. So we're measuring something, right?
Yeah, well, I mean, we
So
are
we
in a
have,
Cartesian box. We're not at all in a real model where we could really have the rotation rate of the sun or anything.
Okay,
It's not the purpose. The purpose here is just to show that with these simple
How
equations.
can you have latitude
Oh,
in
but
Cartesian
wait,
box?
Sorry.
You have a latitude in Cartesian box because you assume that you
Yes,
put your
it's-
box at the surface of the sun. Y represents latitude, Z represents
Because your
longitude, and X
alpha is
represents depth.
antisymmetric with respect to y equals 0, which is here. So this is why you create a magnetic field which will resemble what we
Can I
have.
ask you if you show solution for energy or different slide, you will have infinite growth of amplitude with your variation because it is classical solution.
Yes.
But according this, solar cycle should have more and more stronger amplitude of variations.
That's what
But,
we see here.
Yes, but we observe sometime
yes.
solar cycle.
Yeah, of course, because we have a saturation mechanism, which is not included here. Because we're in a kinematic dynamo, and we are in these particular equations. Well, we'll see after that I modified the alpha effect to have a quenching of this term to make my field saturates. But the truth would be to solve the whole equations and to solve the Navier-Stokes equations
To
as
be
well.
dynamical, yes.
To have Lorentz force feeding back on the velocity feeding back on the magnetic field, then you will have a natural saturation of your.
So you has done this? Or no?
Sorry?
You has done this? You used Navier-Stokes equation?
No, I'm kinematic. So V and alpha are
But
prescribed.
you're using some form of alpha quenching.
Well, in this,
In this
what I
slide,
show
no,
you
but she
here,
could,
no.
yes, we can.
But that's what I did in practice, because otherwise, when I did my minimization algorithm, I had troubles with when I didn't have any alpha quenching, because I had values of alpha which were. Well, I will tell you about
Okay,
this
I'm
later.
puzzled with how we got to know this. What can you show the previous plot? Because butterfly diagram, what determines the shape of?
This.
Yeah, what will have what?
This is
latitude.
Yoshimura Dynamo. This is all stuff. This is Yoshimura Dynamo from the 70s.
Well, you should
But this
is
is
the
this
sign
is even
of-
older. It's Parker's.
No, I mean, this is the principle of the sign.
Yoshimura did this in spherical coordinates.
No, it's the same principle. It's the same principle. It's a multiplication of the derivative of omega times the sine of alpha. If you have alpha times dv over dy equal to a positive value, you get
I'm not questioning
forward,
It's-
or
I
if you
think
get
it's,
negative, you
it's-
get equatorial.
I'm
It's
not
basic
questioning
dynamo.
sign, I'm questioning the shape. Because you can see distribution is latitude. And wondering how I can obtain it from these equations.
Because that's
Right.
Can you show the previous plot again?
So this,
No, that's
it's
what-
naturally what you
you know,
get.
they have this picture where this is,
Diagram
you know, the
of
right.
Yes. Yes.
What determines the amplitude distribution here? With latitude.
the latitude. This is the dynamo wave you're seeing.
Well, how you get from this equation that you showed?
It's what you get.
Yes, that's a standard Parker wave dynamo.
But you use Cassidian coordinate system.
Cartesian coordinates.
Yeah,
How
but
is
it
that?
works.
It works.
I mean, Sasha, what is exactly is the question?
Well, the question is how you get the shape of these, because you can see some,
Well,
that
wait,
it's more concentrated in
I
low
mean-
latitude.
I have another.
This you
plot
get really from
later.
linear theory, right? I mean,
I have
even
a-
Cartesian
Yes,
analysis.
Here, because I changed the sign of alpha.
And you get the polar dynamo.
This is
Standard stuff.
normally what you get. This is, as Sasha said, the product of alpha omega, the sign of dynamo number, which determines the size of direction of propagation of the wave.
So this is actually one-dimensional, this model, right?
No, it's
It's
2D.
2D. So, okay.
But it's Cartesian, right? So
What's
how
the
can
problem
you-
with Cartesian? I mean,
What's latitude here?
come on. I mean, let's stop the silliness here, okay? So, voilà. You take a box. You have as your z direction, z is equal to phi. As your y direction, this is equal to theta. And the depth of your box, if you have one, is x, and that's equal to r. Voilà. That's the coordinate system, okay? You replace r, phi, and theta into x, y, z. Then you have your Parker dynamo. This is a very simple thing. This is a very simple thing. You define and the sign of dv phi, dv dy times alpha. The sign of that, if you want, sign. I don't know how you want to write it, but sign of that quantity will give you either a poleward dynamo or equatorward dynamo.
So it should be symmetrical, with respect to 45 degrees. If
But
you
here
define
we have
theta
put,
is
here we
y.
put 0. Here we put 0, and we have put an alpha that's changed sign as a function
That's
of the
the
hemisphere.
point. Omega and alpha are
No, I'm just wondering
these
why it's not
shapes.
symmetrical with respect to 45 degrees, if you...
I mean, why
if you
45 degrees?
Why determine this?
Why
What do you mean 45 degrees? It's symmetric with respect to 0. 0 corresponds to the equator.
But the wave is symmetrical, right? You have sine y.
It can be symmetric.
Huh?
It can be symmetric. Linear modes are symmetric about the midplane.
How you get a symmetrical mode?
You can excite either dipole or quadrupolar family.
Yes.
And it's a question of the threshold of your Reynolds number. So you can define a Reynolds number above, for the quadrupolar mode and a Reynolds number for the dipolar mode.
Critical,
and
yeah.
whichever is the lowest will trigger the dynamo wave and the symmetry of your wave. And when you are in kinematic dynamo, it's either one or the other that dominates.
So which mode is here on this?
It's antisymmetric, this one.
Yeah, but it's antisymmetric, but it's not a sine y, because you have the sine function, and sine function is not like this. This is y. It's only
Yes.
if you put a sine y, you have a node here and here, or so it will be symmetrical relative to this line.
There is a plus 1, no? In the formula?
It's sine y plus 1 over
Plus
2.
1.
Because if you have,
There is a
this
plus
formula, you have
1.
sine
There is a
y.
sign plus. So that makes the change
This
at
is
0.
alpha. This alpha is cos, so this is y minus 1, 0, 1. So it's just antisymmetric with respect to y equals 0.
Yeah, but it's symmetrical with respect to y 0.5. I'm
1.5?
puzzled because you have solution which is
No, it's not
with respect to
symmetric with
0.5.
0.5.
No, we put a plus 1.
Sine is also it's a symmetrical
No, we
function.
put a plus 1. Look at the formula. There is a plus
I mean, in
1.
other words,
Pi
alpha
over 2, it's a symmetry here. So that's
is antisymmetric about the equator, right?
yeah.
And there's no doubt about
I'm not
this.
questioning this, and I'm just wondering why you have more concentration near the y equals 0 than near the poles.
Oh, yeah.
And how can get this not using spherical coordinates, and I don't know.
I think that's because of the shear, as you can see. The shear is maximum around 0 here. Certainly, you have this transition, so we could look at the derivative of that quantity,
Yeah, it's
perhaps.
interesting to look at it because I don't know how you can make this without using spherical coordinates. That's what
Well, it's what is done in the Stig's book. It's exactly what he does. He shows
I mean,
exactly the butterfly
if the
diagram.
dynamo mode moves,
No.
if the dynamo waves were to move to the pole, if you change the sign, didn't you have such a thing? I think then it's further away from.
If you change the sign of
That's what I
dv
showed.
times alpha,
That's what
you
I
get
showed
poleward
here.
dynamo.
Yes, and then the field is stronger near the poles, etc. You see?
This is a case where you have
No,
dynamo
right?
with-
No, it's not symmetrical. Put 0.5, you can see kind of it's a bit shifted here, but much more symmetrical with 0.5. It's not displayed as much. I don't know.
I mean, first of all, yeah, this is a mixed mode.
Out of
Are you right?
10% of this is 0.5. It's slightly displayed, but much more displayed in the previous solution.
Yeah, I mean, this is not a pure mode. Lorraine, you agree, right? Or is
Well,
it?
It will
I
maybe
don't know
shift
what-
to a
what-
symmetric
what
mode.
did
Yeah,
you-
this is what we.
If you
This is
choose the
simple,
contours to be
Displacement when they use spherical coordinates.
But this will be beside the point here.
yeah. So what's actually the point? The point is not this.
No, thank you, Axel.
The
We are
point is
thinking of something that was
I think we
55
should
or
see
Yeah.
it in a mathematical framework. We're not trying to do reality. It's not the same at all. It's just we are interested in these equations.
data simulation.
Forget about the context.
No, I'm interested specifically in equations, in solutions.
No, but we are interested in data
But
simulation
that-
here.
Solution-
It's a basic
Stick's book solution
solution.
is, I know, Stick's book solution is a sine y and cosine y.
I mean, at this point, I thought we talk about data simulation, right? And so, therefore, this is a model which you simply
Well,
use, which is close enough to.
what we want to do the
Other
data
things.
simulation on.
I mean, if she used the Lorentz model, we can, of course, talk the rest of the day about Lorentz's history,
Let's
for
move
example.
on. Let's move on. Okay. Okay, so this is the solution we can have. So the idea is to write the adjoint code for this for the basic code solving the equations I showed you before, and then to have some way to get the sensitivity with respect to the parameters we are entering at the beginning of the basic code. So this is just what Elias showed us yesterday, that you can through the adjoint code get the gradient of the cost function with respect to the state vector. This. Using the derivative with respect to the final variables, which in this case are a and b.
What is v and u here?
So v in my case would be vectors a and ab.
Can you please write down the cost function in this case?
Yes. You will see it later. So v is ab.
But these are vectors themselves, right? You mean the array, the full array, right? The full A array
Yeah.
as a function of all next points, yes, right.
And this is alpha, omega, eta. So G is my model.
So this is slightly different kind of data assimilation than was described yesterday, because you are basically looking at how the fitting parameters to the data.
It's not
Which was
really,
not what we were doing yesterday.
yeah, it's not the initial conditions here that I will try to get to fit the observations. Really, it's the entrance parameters.
But these are
But it's more or less the same.
The problem is more or less the same. It is just what you differentiate your function of. I mean, what are you trying to find variation with respect to your function of? Your initial state, as I was showing, she's doing with respect to parameters, it's the same formulation, it's just the output you're trying to optimize with respect to.
But we expect that the adjoint equation will be somewhat different, because the dependence of the original G on the initial condition and the parameter can be different. So depending on that, the adjoint equation can look different.
The adjoint equation is the adjoint equation of your code.
Yeah.
Then what you are minimizing, it's what's different. The
Okay,
cost
so,
function will be different. But the adjoint code will be the same, I guess.
Yeah.
So what I'm doing here is I'm in the basic code introducing some parameters, alpha, omega, eta. From the basic code with my model M, I get A and B. The poloidal potential and the toroidal field, BZ, I think it was called. From this, I define a cost function. So, in my case, the cost function will be the errors between B at certain points, so x, I, y, j, t, n squared, I think, minus some observations. So I will tell you after how I get the observations from the same points, something like this.
Not B square, right?
Squared, yes.
So
No,
alpha,
not the
alpha,
square itself.
P minus B
Yes.
observation.
Everything
You
is
put
squared.
the square.
Yeah, it's squared.
but alpha, omega, and eta are
So
constants,
everything is
right?
square.
Yes. Sorry?
Alpha, omega, and eta are constants, right?
Yes, constant in time. But alpha is a function of y.
Arbitrary function of y now.
Well,
Because prescribed
so,
previously.
okay, so wait. In my procedure, what I want is to be able to form this cost function. So to be able to form this, I need to know some observations. So to get these observations, I run my code with particular values of the parameters. So
No, I'm just wondering
Which-
what you mean by parameter. You mean constant or function?
yeah, alpha is a function of y, like sine of y plus 1 over 2.
So you
times
prescribe,
y.
you prescribe as a sine function.
Yes, well, to get my observations, yes. It's prescribed, yes.
That you're trying
It's
to...
prescribed
So
everywhere.
what is the parameter here?
Alpha 0, omega 0, and eta.
Yeah. No, it's well.
It's
yes.
coefficient in this equation for alpha, this parameter, or
It's alpha. It's
Or the
the
whole
whole. I
function.
can have the whole function.
so it's arbitrary function. You consider for arbitrary functions.
Yeah.
now.
So aren't you trying to find the optimal form of alpha? Probably.
Yes.
Fit
I
your
will-
observations.
the idea will
Yes.
be to run my basic code, get the cost function, minimize this cost function to get back to which parameters were used to create my observations.
So you start with wrong parameters,
Yes.
not the same in your simulation,
Yes.
and then you minimize with respect to these parameters and
Yes.
try to retrieve them through your
Exactly.
simulation procedure.
Yeah.
What's very powerful is that you can retrieve, as you know, the shape, and not just the alpha 0 in front of the formula. You can find the alpha 0 plus the dependency. And that's what's interesting, because you can then use that to invert profiles that you don't know.
Right, so the idea was to begin with an alpha ops, omega ops, and eta ops, which give me the b ops. So I know them, I know how I got the observations.
You just simulate this observation.
I simulate the observation, it's a twin experiment.
How you simulate this? How you simulate observations?
By
By
choosing
exactly
separate
what I
parameters.
said, by choosing alpha, omega, eta, for example, what I showed you before, same model. I choose the function, I choose everything, and I get b everywhere. So then I can choose what observations I want. So I can choose how often I take my observation, how at which points in space and at which points in time I have observations.
Observations of what?
Of the magnetic field.
I mean, at the moment it seems the B, right? And B is a toroidal field.
It's
Yes.
toroidal.
Yes, so that's observation.
No, but
Can't do it.
it's just an
observe
experiment. Just an experiment. We're trying to see if the adjoint code works for this particular model, which is just a set of PDEs. That's
Also,
it.
artificial data you generate. Some.
Yes, I generate my data, so this is
Okay.
not physical at all.
This
we
is
can't
called,
make the
called
sense related.
twin experiments, and it's the best way to validate your adjoint procedure. There are two things you're supposed to do. You're supposed to validate the adjoint, the tangent linear code by comparing.
Yes,
We
but
didn't talk about that
I
last,
will
you
come
know.
to this.
So as you know the observation from a simulation, why are you using square? Why not use b minus b observation modulo square?
Well,
Yes.
because I try to do this, and as b changes sign and b up also changes sign.
Yes.
I don't know, I had troubles with this, but maybe we can also use it. It's not very important. I think.
Actually, there's one point there that exactly how you choose a cost function is independent of your physical problem. But it is dependent on is the statistics of your errors. So, for example, you could, in some situations, it could be B. In other situations, it might be better to log B as your cost function.
What I mean here is that assume you are trying to reproduce the butterfly diagram in some way, and due to a phase difference between the original the code you ran initially to match your data, and the one which you are using for data assimilation, you may have phase difference between the B on the north and the south. Am I making any sense, or shall I say it again?
Yeah. I mean, you mean we want to have B? We would like to have B and
I'm saying
not
you run the code
energy.
once. You run the code once. That's your observation, right?
Yeah.
And then you have B in the north and B in the south. Now you are running the code once, basically the adjoint code, to find the right parameter which fits it. But now it turns out that you have actually the field which is just phase inverted from the other one. So this will show up as an error if you are not using the squares. But it will not show up as an error if you are using the squares. You see what I mean?
So it is unobservable, which is...
Whether the dynamo with plus or negative field is the same problem.
But it may give you a different dependence of alpha and eta on time than the one you originally started with.
But at the end it doesn't make any difference.
But therefore she could have done what Jouve suggested. So it's actually strange that it makes a difference for her. You're saying that one works, the other doesn't actually.
Well,
That's what you're saying,
maybe
right?
I didn't
I mean, maybe,
investigate.
yeah. But on the other hand, I mean, what she had probably in mind that she wanted to model sunspots, right? And sunspots really care mostly about B squared,
Of course, yes.
right?
Yeah. Well, it was really the.
Yes.
I don't know. Just we're trying to minimize
Yeah.
the square of the energy. Yeah, maybe it's not a good choice of the cost function.
No, I think it makes some sense. Sunspots, right?
Okay, so this is it. We have our cost function, and now we want to have through the adjoint code the gradient of J with respect to these parameters, alpha, eta, and omega. So this is what I did. So this is just to show you quickly. In the direct code, we use a module which calculates the spatial derivatives. So this is just, for example, derivative in the x direction. So this is just the instruction which defines the first derivative. And we need to look at the tangent linear code. So this is what is shown here. This is linear, so this is the same. The tangent linear code is the same for this particular instruction. And this module is introduced in the main program. And in the main program, this is at the end, we have our cost function, which is dependent on B. So this is what I showed you here. This is in the main program. This is the tangent linear version. So in this case, you just differentiate this instruction.
Your evolution equation is linear. So the nonlinearity, the reason you need a tangent linear part comes because the cost function is nonlinear. Is that right?
No, I don't think so, because it's not really in the sense linear is not really in the sense of the equations being linear. If you have, I think if you have in your equation we have, for example, dA over dt of alpha b, this alpha will, this will be a part that you will have to write as something different in the tangent linear code. Because alpha will, if you want to assimilate to get the alpha naught, for example, if alpha is alpha naught alpha prime, then you will need to get the derivative of J with respect to alpha naught. And in this case, you will have to differentiate this in writing that it's alpha naught basic alpha prime basic B. So plus things. This is maybe not very clear, but
Yeah, I didn't understand. I didn't understand this for.
If you just have an instruction which is A equals BC, the tangent linear code will be delta A equals delta B C plus B delta C. So as soon as you have multiplication or anything like this, you will have to write your tangent linear version. So this is what I'm doing here. You have, yes, well, in this case it's really nonlinear, but you have b squared, so that's why you need to differentiate it.
Yeah, but then you have another b minus b ops squared out of this. Why is that? B ops squared.
Yes,
b squared minus b ops squared.
because what I call BB here is the basic, what they call the basic B. So this this BB in the adjoint code, which will be the B which comes from the direct code. You take the same values.
I see.
For B and C here, for example.
So which one now again? BB was the which code? Which BB?
BB is B.
Yes.
Which comes from the direct.
And B is the other one. Yes.
I mean, in what was presented yesterday, BP seems to be the like the state which you are finding a perturbation around.
Yes.
Yes, like here. Yeah. So yes, I think you will always have to write tangent linear code, even if your equations are linear.
So you mean so B is actually the same as delta B, and BB is the same as the other B.
Yeah.
Yes.
Yeah.
So what I meant is your del 1x on the left column and the del 1x on the right column are the same.
No, because this is a constant. This is as if I wasn't not doing anything. So here you don't have any
Multiplications.
Yeah, you just have an addition, subtraction of two terms. So if you
Write it
if
for
you
A,
yes,
B
and
minus
plus
C.
C.
Voilà. That's
Delta A is delta B equals delta C, so it's the same equation in fact.
But for you have your observation. Do you have a tangent thing for the observation as well?
No.
What? No.
No,
Because the observation operator implied here is identity. That's what is implied in your.
Can you maybe just it helps maybe
yes,
just
because the observations are really values of B, which is an output from the basic code. So if I would write it in terms of the H operator, right? My H would be the identity.
So when you're saying xi yi in the cost function, you're using xi yi as all points on your two-dimensional grid.
Yes.
Yes, well, this is left to my choice. I can have only 2 points in space where I have observations.
Yes, but then your H will change. It will no longer be identity operator.
Oh, right. Yeah. Yeah. You're right.
No,
Yeah,
it
if
will be
H-
identity operator acting on the state, that particular point.
No, because see, the dimension of y will then be just 2.
Yes.
And the dimension of x will be nx and y.
Yes.
So H has to reduce nx and y to 2.
I mean, the way I would look at this is this, that this is the sum of terms, and that sum is like the first term b squared. It's in my terminology yesterday. That is basically h of the state, h of x, or the h of x is your function.
Yes, right.
Yes, and you can have 1 to n of those observations. If you choose, let's say, one observation at each point, then the number of observations will be equal to the state dimension.
Yes,
But
and then H is identity.
Yes, H refers just to what you have got. Let's say localization, which refers to each point where it exactly is taken. But even if it doesn't apply to the whole state and just the one state, it's still an identity operator. It's just given a certain state at a certain point in time, a certain place, you apply the operator, which is just identity.
H is just how you go from a point going from the model to a point which is an observation. So at each point, at point x, y, y, j, t, n, to get an observation, I take B at this point. So I think.
One thing I still didn't understand, you have this 4 B, 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 and then the rest. So I would understand the 2 B, B, B thing.
No, the whole thing is to the power 4.
Is squared, everything is
square
squared.
goes square.
Oh, the whole thing is squared.
Maybe
Ah.
I forgot the square.
Sorry, I missed that. Yeah, then everything is okay.
No, you have the square right.
Yeah, it's
Yeah, yeah,
okay.
sure, yeah, I missed the second squared, yeah.
Okay, so so for me, what it just the tangent linear code is not I just wrote it on a paper to be able to derive my adjoint code. I don't really need my tangent linear code here. I just run my basic code, which solves A and B and which forms the cost function, and then I wrote the adjoint code. Thanks to the tangent linear code, I didn't really had to code it.
What do you mean? I mean,
The tangent linear code will never be run.
It depends a little bit on.
But it depends.
I mean, there are situations where you don't need the tangent linear code, because what you do is that you run your model forward once at full resolution, comparing that with observations each time. You calculate as you go forward with y minus h of x.
So this will be sequential assimilation.
No, I'm talking about a window.
Okay.
So the 0 to tau. So you run your model forward at full resolution, comparing the model output through the observation operator with the observation. So you collect these h of x as you go along. You got those at full resolution. Then you run an adjoint with h of x as input as a forcing term in the adjoint equation. Now, the reason why you don't need to run the tangent linear in this case is because you already there is no let's say perturbation in the forward equation because you are doing adjoint with the same resolution. If you would have been running, let's say, the adjoint that minimization at a lower resolution, then your h of x would have been h of x background plus some linearized state times perturbation. And to get this linearized observation operator times perturbation, you need to run the tangent linear at a lower resolution.
Okay.
So you have the choice here to run, if you are doing everything at the same resolution, you have the choice to use tangent linear if you want to, or you just use a nonlinear model directly because you have the output. So that's
still somehow. Can you explain it maybe?
please.
Now, what he says is that the tangent linear code is used only if you want to run your simulation. If you want to do the minimization loop, what he called the inner loop in his slides, at lower resolution in order to reduce the cost of going back and forth. Then you will need to use this tangent linear model to actually know the low resolution bit of your run. But if you are able to run back and forth at the same full resolution, then you can avoid that intermediate state.
Because it's not a very costly computation.
We are not
to
doing
do
costly simulation here. But let's say if you are doing a 1,000 cube simulation,
Yeah.
then perhaps you want to do the back and forth loop for the minimization at a 200 cube.
I mean, but that really just means either you do get the tangent or you don't. I mean, you never get
You
the tangent
always
if you
have
don't
to-
calculate it, right? Or do you get it actually
No, but
from the
you
from two
use
runs?
You use the tan to get the adjoint equation and you actually solve that.
But he says you don't.
Yes, I need
No,
to
no,
write the tangent linear code to be able to write my adjoint
Adjoint.
code.
But she never uses it.
She don't use
I mean to write it on a paper.
Yeah, but why don't you run it? I mean, that would tell you then the gradient.
Yeah, in my minimization algorithm takes j and the gradient of j to minimize j.
Right.
J is given by my basic code. The gradient of j is given by my adjoint code.
Yes.
To calculate the gradient, what you need, actually I got some other notes on that. What you need is the value of this adjoint variable at time 0. That's what you need as an input to the gradient. That in some terms depends on the background error. So you get that directly just from the adjoint integration. So that's
I think it might really help.
Oh, in the way as you explained yesterday with
Yes.
these little h's, yeah?
yes.
Is that what you're doing then?
What?
No, he doesn't know what do you mean.
No,
I mean, he was
I don't-
talking yesterday about evolving the capital H transpose by multiplying the little h transpose in reversed order, right? That's what he explained yesterday.
Yeah, but that's in the adjoint
Yes,
code. You
that's-
always do that. That's a way of writing an adjoint code. You
That's
always go
adjoint code.
backward.
Yeah,
So
but then
that's what
that
we
way,
did. Of course, you have to do
I
it
think
that
it will
way.
really help
Yes.
if you write down
So
the.
you
I
don't-
can,
right.
yeah, I can.
If you write down the original equation, the adjoint equation, and the
No,
tangent linear equation.
We're not going to go through all that.
no, but
No, because it's
all
not
we
really
need is
the equation which is important, it's the way you solve it in your code.
Exactly.
Each-
we
each
told
in-
you that yesterday.
Each instruction has an adjoint instruction. So what I can do is, for this instruction, write the adjoint instruction.
yeah, which you did, right?
No,
Isn't it?
this
No,
is the
just the
tangent.
tangent linear part.
So wait,
Ah, okay.
I will
Uh-huh.
do it again maybe. So this is an instruction at the end of my basic code.
Mm-hmm.
I finished by this. So let's say we just have 1 point. The tangent linear instruction will be what I showed here. So I call it maybe now delta J. So I differentiate this. So it's 4 delta B. B, maybe basic B, if I can, if it's clear for you, I
Mhm.
call it this. And then, is that right? And then I have B squared minus my observations, which are a basic observation as well, but it's just the same.
Yeah, you can just skip the little b, I think, because you defined it earlier. It's the same thing, isn't
Exactly.
it?
So let's write it this
Uh-huh.
way.
Yes. Yes.
So in practice, this B and this B observation come from my basic code. I save them at
Yes.
the end of the
Yeah.
basic code.
Yes.
When I enter the adjoint code,
Uh-huh.
beginning with this instruction, which was the last instruction of the basic code. The first instruction of the adjoint code should be the adjoint of the last instruction.
Uh-huh.
When you do minimization, you minimize each point, right, at each time. Because it's, J is a function of x, y, and t, right?
Yes. Yeah, in this case, I just assume I'm looking at just 1 point because I didn't want to have the sum. But,
Or you minimize, the whole solution. You take integral of these, you take integral of...
yeah, you
Over
sum,
x, y,
you
and
sum
t.
everybody.
You take sum.
Yeah. You minimize the sum of all the errors.
So it should be sum here.
No, because she decided to do it only for 1 point.
Yes.
Yeah, we,
One
we
point.
have a sum. We have a sum. But
then
in this
the
case, I
sum-
just want to write it to be a pedagogical. We don't need to add.
Because the sum is more complicated than this.
Yeah,
It's
but
the
that's
sum of this.
it's clear then, I
Because you
think.
have cross jobs.
Sure. Yeah.
But you eliminate all higher order terms.
Yeah,
and go
yeah.
away.
Anyway, so this is a tangent linear instruction. Okay, and now my adjoint instruction. So this will use the mechanical way of having the adjoint instruction when we have the tangent linear instruction. So this is well explained in the paper I gave you, Axel,
Mm.
by Olivier Talagrand. He did something on this where it's very well explained how you get your adjoint code when you know the tangent linear. So what we have to write here is will be delta B star now. The adjoint the adjoint variable is delta B star. You always have this plus
Capital B.
delta J
Capital B.
what? Yes, times what multiplies delta B in my tangent linear instruction. So it's 4b squared. Ah, yes, okay, I see what you mean. Sorry. This is the adjoint instruction. And then what we do in the adjoint code is put this to 0.
So that was the most obscure part for us. Or you did explain it a little bit, but the way you have to put things to 0 sometimes was not completely clear to us. But
Okay, so
sorry. So in the adjoint code, you basically just delta b. If you set delta just equal to 0, all the terms disappear, right? On the right hand side.
no. Well, you begin with so this star means gradient of j with respect to this variable. So delta j star means delta j over delta j. Delta b star means not delta, partial derivative of j with respect to b. So when you enter your adjoint code, you begin with delta j star is 1.
And then when do you set it to 0?
Oh, because I don't know exactly why.
that you can explain. That was the
I
hardest
didn't say
part.
why, I said when.
When you put it to 0
Answer purely.
after you put it to 0 after you
used it.
used it
You used it.
for this particular instruction. If for example I had plus, if I had also a in this, for example, I would have the same expression but with a. Would add this. A carré.
But yeah. So that's really the
If I
business
had
that you
this,
explained yesterday, really.
I would also have to write before setting delta j to 0, delta a equals this, but for a.
I mean, yes.
And then delta j star equals 0. So this is just how you will derive your gradient for every following variables then, because in the instruction just before j equals this, you have the b equals something. You see, so in the adjoint instructions, you will have something else here. It's, for example, dj over d alpha, which is d alpha star, will be some function of delta b star, which was defined just before. And delta j star was defined just before. So you, in fact, you just...
Correct me if I'm wrong, this adjoint equation is the one that you evolve backward in time, right?
Yeah.
So, first you run the code to generate your observation,
Yes.
and then you run the code again, this time to compare with observations from say T1 to T2.
With a different
Yes,
parameter.
with some guesses, because apparently
Exactly.
we don't know that it was done by the same code. We reach the end T2, and then we start evolving the adjoint equation backward
To get the gradients.
from
Yes.
T2 to T1. And then when I do it backward, so when I take the backward step, first step from T2, this B that you have is actually B at T2.
Yes. B at the end.
Yes.
At the end from the first code.
Yes.
Okay. And when you come back, I mean, by doing the first code, were you storing the intermediate values of the code B that will be useful again, or
You save B everywhere. Yes. Everywhere at any time.
not from the, nothing to do with the observation actually? Just
No.
when you are running the, for example, if you have been doing it for a huge system, where this going forward and backward would be done by a smaller coarse-grained code, you would still be saving the B at every forward time step.
You can do it in two ways. If that is one way. If it's too inefficient, you store the intermediate times,
Yes.
and then during the adjoint integration, you can actually run and fill in.
Okay. But these are the intermediate times where you have the actual observations.
No, you have to store each time, because you always have to step the adjoint equation backward at each time step.
So when from T2 you go to T2 minus delta T,
Yes.
then you use the B forward of T2 minus delta T
Yes.
to go to T2 minus twice delta T.
Yes.
Okay, excellent. Thank you.
And what is A as opposed to B? Is that
Oh, it's the colloidal potential.
Oh, really?
I was just
You do that
wanting
one
to
too,
tell
yeah?
you that if I have more than one
okay.
dependence here, I will have to write another instruction in my adjoint code.
Before setting delta G star to 0. That was just to answer the question.
Yes, I see. Yeah. Mm.
Right. So through this, you and you end up with these values: delta alpha star, delta omega star, delta eta star, and which gives you the gradient of J with respect to the entrance parameters of the basic code.
Can I just say one thing? I mean, if I compare this with what I did yesterday, this situation, I had like two terms, like this background term, this observation term, minus a to x. In this case, you're just taking the background term. No, the observation term.
Yeah,
the background there is not. So just observation term. So when you integrate it back with the time, you are collecting up this contribution of observations, h transpose r minus 1, y minus h of x. You're collecting those up. That is why you, in this case, use the terminology, you go directly and say this is J here. Actually, in actual sense, you are taking the transpose of the observation operator, but in this particular case, that is just one term in the expression J. That is why the J comes in there. In general, J would not come in there in the adjoint integration as such, because J would contain also background error contribution. So that is like, okay, you could take it as an observation J. So you would have you would separate it into cost function for the background, cost function for the observations. But it's just, it maps basically one-to-one what we said yesterday. It's slight different in notation, but it's the same.
Right. So I hope that in doing this, minimizing my cost function, I will get back to the basic parameters I was using to produce my observations. So this is what we try to look at to see if the adjoint code could be validated. Well, maybe what I forgot to tell you is that I developed the adjoint code by hand, but then you have some automatic tools. Maybe you evoked this yesterday, but I use an automatic tool which is called Tapenade, which is developed in INRIA, an institute in France. And with this, it's very convenient. You just introduce your main routine, your subroutines. You tell the tool which are the main routines, everything, and it just gives you the adjoint code. Just like this, wonderful.
So we were able to verify our adjoint code.
So with this, I could see that that we did a lot of mistakes in the adjoint code, but it's very convenient, probably for codes which are simple like this. I don't know for more complicated ones.
I have just some confusion which maybe you'll be able to clear up. Yesterday when we were doing data assimilation, the emphasis was on error. So we were basically minimizing cost functions, and we were assuming that the errors have a Gaussian distribution, and the cost function, where the cost function was written, was basically reflecting that. Today I don't see a role of error into the problem, and it's just not clear to me how do I...
Well, if you look at this, actually, when you write this, the errors are implied. The error implied there is that the error of b squared has unit 1. In this case, the observation operator is b squared, That is observation. You're not observing b, you're observing b squared, if you look there. And you're dividing by this with r minus 1, if you put sigma. See, just assuming it is 1 everywhere. That is implied. If you write nothing, you actually imply that it is 1. And if you take this connection between this and the Gaussian framework, you are assuming that the errors of b squared are Gaussian errors. That's how it maps. With a variance of 1. If that is true, if it works, we don't know, but that is the assumption behind this.
And the error in the initial condition is not being considered.
It's not being considered here.
Yeah. So maybe I can show
but
you.
the errors are still assumed to be Gaussian.
Yes.
So this is the first test I did. So what I did is that I had I assumed I knew omega and eta, and I tried to get only alpha as a function of y. So I have 30 points of discretization in the y direction. So I have my dimension of the gradient of j will be 30 in the end. So I have 30 parameters to adjust to get to the right solution. So this is the result. The thick curve is the right answer, because I know the right answer, as I produce myself the observations. And the other curves are the alpha obtained after the minimization for a different tolerance value on the gradient. So this is an input of my minimization algorithm. I can tell the algorithm if the gradient is below epsilon, then it's finished. I attain my best value. So this not very nice curve, the dashed one, is when my gradient has reached 10 to the minus 3. I have alpha, which is very spiky everywhere. Well, it gives something which is not very, very nice. And my initial guess was something different, a straight line. So yeah. Okay, so I changed my alpha to get this. If this is 10 to the minus 5, I get to this other curve here, which is here. So it fits a little bit better the true state. And then I go to 10 to the minus 15, and then it's more or less superimposed with the true state. So I go to the true state in this case.
The x-axis is latitude.
Yes. Yeah.
So it seems it takes the longest to converge at the equator, where
Yes.
it changes sign.
Yeah, exactly. So I think the reason is that I looked at the values of the gradient in this area, and the value of the gradient is very weak compared to the others. So it means that my cost function doesn't depend very much on the values of alpha at this.
Because with this B and B observation, both are very small near the equator.
Yes. Yeah, because they also change sign. Makes sense.
But you could actually get around.
I was going to say that this has been done with regular sampling of the latitude. If now you decide to, okay, you have some understanding and you decide to collapse most of your points toward that region where you have difficulties, perhaps we will get a faster convergence.
But
This has to be checked.
there's another aspect of this, which is we discussed this yesterday, that you have assumed error 1. Now, it is if the b varies, or b squared, which is, we are actually looking at b squared, if that varies by orders of magnitude, then maybe it is not reasonable that the observation error should be 1. Maybe it is more that it should be 10%. So that means that sigma, the observation error, would be smaller where b is weak. So b divided by sigma, b squared divided by sigma would be larger, and this would take faster to converge there because you give more weight to it in that particular region.
It's similar to what kind of you were saying yesterday in finding minimization.
Exactly.
When you kind of have a symmetric error structure in the
Okay, so what does that mean? That means that you have to have a kind of a covariance matrix where you have the points you have chosen to do your observation, your artificial observation, and you need to have the value of the assumed error that change as a function of position.
Well, it depends on the variable. Like, if you have a variable which is fairly, I mean, you're assuming things here, and we're just talking about what is a reasonable assumption to get some good out of this example. And if B is fairly constant, B squared is fairly constant, like if temperature in the atmosphere varies by a small amount, a few, 10% maybe, 10-20%, then having a constant error is a reasonable assumption. Sigma equal 1 may be different. But if you have orders of magnitude difference, then maybe, I mean, there is no reason to expect that the error should be, if observations value, there's a 0.1 and 10, and the observation error is 1, that's not a good observation error for both of these things. So 10% would maybe have been a better assumption in this particular case.
Yeah, but that means that you need to have some way of putting your errors
Yes.
as a function of dependence.
You put sigma of
xy,
xy
and yj, yes.
But it can also be just simply a function in variable space, as a function of the value of the variable itself. It doesn't need to be a spatially dependent. You can make statistics, that's how we work. We make statistics, for example, for humidity as a function of relative humidity. And we know that errors vary. So when we tend to -4, when we have 4 orders of magnitude smaller values of humidity, we also have much smaller errors. We don't assume the same errors for both.
Well, we can try that.
I don't know, because in our case, it's this case that I used. So it doesn't vary very much. This is 2, and this is 4.
No, he's speaking spatially, not temporally. And spatially, you see with your contours, look behind. Spatially, you clearly see that spatially you have a variation given by your contours there. So perhaps near the equator, the fact that the value dropped is giving us some troubles, and perhaps we should increase the error bar there or decrease the sigma to make it give more weight in the minimization procedure.
Yeah, because it takes me a very long time to converge in this guy.
I mean, usually what people do is like they have if in these kind of situations where it varies a lot, you have like a percentage, but you cut it off at a lower value. I mean, you go to some reasonable lowest value. You don't go below that, because you go below that, you will end up in some numerical troubles anyhow. So, if B is 0, then you don't want to be there. So it's just you have the lowest value and then increase as a function of amplitude of B squared, for example.
Alright, we will try that. So one thing we haven't done now is... Right now, of course, these are twin experiments, and what we have done is that we only have done a regular sampling of alpha over the latitude. But then you can say, I only have observation in the northern hemisphere, and you can put your points in only in the positive part of y, from 0 to 1. And you will be able still to try to, you will do certainly a good reconstruction of your alpha in the northern hemisphere, not as good in the southern hemisphere, but you can get information on the southern hemisphere even though you only have observation of the northern hemisphere. So that's the things you can play with these things.
Yeah, change the sampling of the observation.
And typically with the sunspot data, if we want to go back to real things, we know that we will have information only in the active band. So from -30 up to 30. So then we will have to do a test where we put our points only in that part where you observe, and you can get information in the polar region when you don't. You see, so that's the way you can play tricks, and that we haven't done yet. We expect to do that this week if we have time.
You have preempted half of my question.
Okay.
The other half is basically about time sampling. So in the observation, how often do you, within a cycle, how many observations do you have? 10, 25?
Oh, within cycles.
Rough idea.
No, I have very few, so I have an observation every every 100 iterations.
So within a
So
cycle, it's about,
within a cycle,
about 10,
No, less than that.
maybe 5.
yeah, because it's the number of iterations
Yes.
here. So,
Say we get 200 or what? 300. The cycle is 300.
yeah,
3
so
points.
three,
perhaps.
2 or 3, yeah.
Okay, and
Per cycle.
if you take more of them, will it converge faster, or if you take less, will it converge longer?
Probably. Yeah, I haven't done a lot of tests for the
Sorry?
moment, but
If you take too many of them, you will not converge faster.
Yes, but if you take too less, it may still converge badly.
Yeah, if you take too little, yes, yes.
because you mean it will saturate at the moment, or why do you say if you take too
Now,
large?
in your particular framework, yes, if the more you take, the better. But when you have got the situation where you have got let's say, the two components, like the background and observation, there's two components for the initial condition, things like that. If you have too many observations, too dense, that can make it very difficult for the background to converge. And background is what you're interested in. What you will think is that with a lot of observations in a small area, you put a lot of weight to that. Try to optimize that part. Don't care about the rest. So, small part of your region is maybe fine, but the rest is just not fine. So you will overemphasize one particular region if you have too dense observations in one region.
I guess that's all.
I think so, yeah.
Thank you. So what does Irina think about all that? Because you have tried similar things, but on a zero-dimensional model.
Yes, I'm wondering about two main things, about two things in this simulation. The first, I see what really amplitude of variations change twice from begin to end. If you look on left hand of your fluctuation, you have a number like 2. But for right hand, amplitude changes until 4, maybe a little bit more.
In time, you mean?
Yeah. It is a dangerous way, because if you have per cycle just only 2 observations, really you should have very strong error in this case, because real amplitude
It's not at the top
yeah,
natural
yes. And second part, I don't